Hello, my dear children. In the class of nuclear physics, we are going to study nuclear reactions. Children, we have just finished studying binding energy curve, and there we have seen that very light nuclei and very heavy nuclei, which lie in zone 1 and zone 3 of the binding energy curve, have very small binding energy per nucleon. Their binding energy is less than 8.5 million electron volt, which is the average binding energy of all the nucleons of all the nuclei. Well, since these lighter and very heavier nuclei have lesser binding energy, therefore their stability is less. And in order to gain stability, they execute two different types of nuclear reactions. One of them is nuclear fission reaction, the other one is nuclear fusion reaction. So let's begin the day with nuclear fission reaction. Well, in nuclear fission reaction, children, a big nucleus breaks down into smaller nuclei. But this breakdown takes place only when a particle, an energetic particle, hits the nucleus. So what is nuclear fission? Breakdown of heavy nucleus into smaller nuclei when it is bombarded with energetic particles. When a heavy nucleus is bombarded with energetic particles, it breaks down into smaller nuclei. The phenomenon is called as nuclear fission reaction. And these energetic particles which bring about the cleavage of nucleus into smaller nuclei of nearly comparable sizes are called projectiles. The projectiles are the energetic particles which bring about nuclear fission. Some of the popular projectiles are here. Proton, H11, that's how proton is written in nuclear reaction. It is one of the many projectiles. Well, neutron is another projectile. Alpha particle can also be a projectile. It is written as He24. Beta particle is another projectile. Positron is a projectile. This is gamma particle, gamma photon. It also acts as like projectiles. And children, all these projectiles, mostly the charged one, the charged particles which are used as projectile, they are produced by cyclotron. Cyclotron is a charged particle accelerator. Well, this beta particle is produced by betatron, another charged particle accelerator. So these charged particles are produced by a machine which is called cyclotron or betatron. Well, there are many nuclear fission reactions, but one of the most important nuclear fission reaction I am going to discuss right now. And this is fission of a uranium nucleus with a neutron. When a uranium nucleus whose atomic mass number is 235 is bombarded with neutrons. Remember, these neutrons are slow neutrons. Well, when these slow neutrons collide with uranium nucleus, krypton, barium and 3 neutrons are produced along with emission of 200 million electron volt of energy. Children, this reaction is initiated by slow neutron. So slow neutrons have their energy close to 25 kilo electron volt. So energy is very, very less. So these slow neutrons, when bombarded with uranium nuclei whose atomic mass number is 235, well, 3 neutrons are produced along with krypton, barium and energy which is nearly 200 million electron volt. Well, because of one neutron colliding with the nucleus, 3 neutrons are produced. Therefore, this reaction is a chain reaction. Well, this is uranium which interacts with or when collides with a neutron, 3 neutrons are produced. Yeah. And these 3 neutrons will collide with another 3 uranium nuclei. in every fission, there would be 3 different neutrons produced. 1, 2, 3. Yeah, this way. The number of neutrons which were initially 1 became 3, and from 3 they became what? 9. And all these 9 neutrons are going to again bombard with 9 different nuclei, and 27 neutrons are going to be produced. And these 27 neutrons are going to hit upon 27 different uranium nuclei, and that way 81 neutrons are going to be produced, and these 81 neutrons are going to collide with another 81 different nuclei, and 243 neutrons would be produced, and the process will continue. So number of neutrons increase in geometrical progression like this: 1, 3, 9, 27, 81, 243, and so on. Children, let us understand the situation or the condition under which this chain reaction is going to sustain itself. Well, when this nuclear fission reaction takes place, it takes place throughout the block of uranium. This is a block of uranium. This fission reaction takes place throughout the block of this uranium fuel. And what happens, since the reaction takes place throughout the block of this uranium fuel, therefore neutrons are produced throughout this volume. As the result, N, the production rate of neutron depends upon the volume of the block. So how many neutrons are produced by virtue of the fission taking place in a block of uranium depends directly upon the volume of the block of the uranium. So this N, the fission rate or number of neutrons produced per second, is directly proportional to volume. And the volume of the block, if we take its radius as r, and we assume that this block is spherical in shape. So r is the radius of the block. In that case, the volume is going to be 4 pi by 3 r cube. N is directly proportional to 4 pi by 3 r cube. That simply means N is directly proportional to r cube. And if we remove sign of proportionality, we put up a constant. N is equal to K1 times r cube. So this is production rate of neutrons, which is directly proportional to r cube. This r is average distance of different point masses of the block from its center of mass. If it is a spherical block, then of course this r is going to be what? The radius. Well, some of the neutrons which are produced throughout the block, of the uranium, they are absorbed by what? Different other nuclei which are not identical to uranium, or say impure. There are some impure atoms or nuclei in the block. So these impure atoms or nuclei, or foreign atoms or nuclei which are present, they absorb these neutrons. And since these impurities are scattered throughout the block of the uranium, therefore the absorption of neutron, that is absorption rate of neutron, is directly proportional to volume of the block. A is directly proportional to r cube, or A is equal to some constant times r cube. This A is absorption rate of neutrons. Well, the neutrons which are produced throughout the volume, some of them are absorbed, and some of the neutrons leak to the surroundings. Some of the neutrons come out of the block. Through the surface of the block. These are called as the neutrons leaking. This is called leakage of neutrons, and the neutrons move out of the block through the surface of the block. So how many neutrons are leaking to the surrounding, that depends upon the surface area of the block. And children, these neutrons which are leaking, they do not take part in further fission reaction. Like those absorbed one, they do not cause any further fission. The neutrons which are leaking to the surrounding, they also do not participate in any fission reaction. And the leakage rate of the neutron, which is directly proportional to surface area of the block, is directly proportional to radius of the block. If we remove sign of proportionality, we get a constant K3. L is equal to K3 times R square. Well, a block of uranium is said to be of critical size. Yeah, a block of uranium is said to be of critical size when number of protons, number of neutrons produced per second, that is production rate of the neutron, is equal to the number of neutrons absorbed and leaking from the block to the surrounding. So the leakage rate and absorption rate, if their sum total is equal to the production rate of the neutrons, then what happens? The nuclear fission reaction just not proceed ahead, or it just proceeds ahead. So for the block of uranium where leakage rate and absorption rate, the sum total is equal to the production rate of neutrons, these blocks are said to be of critical size. N is equal to A plus L, N minus A upon L is equal to 1. For N we can write down K1 times R cube, for A we can write down K2 times R cube, for L we can write down K3 times R square, and that is equal to 1. We can see that R square cancels out with this what? Yeah, the power of R3. What do we get? K1 minus K2 upon K3 times R. That is equal to 1. K1 minus K2 upon K3, the constants are written as, are replaced by another constant K. That simply means Kr is equal to 1 or K is equal to 1 upon R. So for any block, if K is equal to 1 upon R, then the block is said to be of critical size. Critical size. And for the block, uranium block of critical size, nuclear fission reaction just proceeds ahead, or just propagates, or say just not propagates. So what is the condition under which it proceeds ahead and it doesn't proceed ahead? We are going to deliberate on that. Yes, children, what is subcritical dimension? We have just understood a uranium block is said to be of critical dimension when production rate of neutron is equal to sum total of leakage rate and absorption rate. And if production rate happens to be less than sum total of absorption and leakage rate, in that case, this nuclear fission reaction is neither self-sustaining nor self-propagating. Since production rate is less, therefore always there are lesser number of neutrons required to carry forward the reaction. So reaction doesn't proceed, reaction doesn't propagates, or reaction is not able to sustain itself. The uranium fuel, which is enriched uranium, is always converted into subcritical dimension, and in this subcritical dimension it is safe and stored. So even if the slow neutrons from outside are going to strike upon it, there is going to be no fission reaction. So if uranium block is of subcritical dimension, it is safe, and in this dimension only enriched uranium is stored. And finally, supercritical dimension. A block of uranium is said to be of supercritical dimension when the production rate of neutron is greater than sum total of absorption rate and leakage rate. And what happens as the result? Always there are some neutrons left to carry forward the fission reaction. So if the block is of supercritical dimension, well, the block of uranium is very, very dangerous. And in this block, the nuclear fission reaction is both self-sustaining as well as self-propagating. And if the reaction continues on its own without any control over it, it is termed as atom bomb. So what is atom bomb? We are going to discuss. So children, let us know what is an atom bomb. Children, atom bomb is a device, is a nuclear device or an atomic device where uncontrolled fission reaction takes place. Well, this is a compact unit. This atom bomb is a compact unit. And what is there? in the compact unit we have blocks of uranium. And all these blocks of enriched uranium are of subcritical dimension. Otherwise, the fission reaction will start itself. And these slow neutrons are available in our atmosphere also. So, all these blocks which are of subcritical dimension are packed together with the TNT. TNT is a well-known explosive, trinitrotoluene. So, this compact unit has right at its center TNT, trinitrotoluene. And when this compact unit is dropped at any place, what happens? This TNT blasts, this TNT explodes. And because of the explosion of TNT, these uranium blocks of subcritical dimension break down. And what happens as the react? As the react, some of the blocks which move into supercritical dimension, for them this chain reaction is self-sustaining and self-propagating, and that chain reaction continues until that supercritical dimension fuel is exhausted, and in the process huge amount of energy is released, and which causes a lot of loss of life as well as property. Well, this atom bomb, well children, it is very, very dangerous, a very, very lethal weapon, and it has only been used once in Second World War. In Second World War, at Hiroshima and Nagasaki, this bomb was dropped, and those bombs were little boy and fat boy, and there was huge uranium in quintals in those bombs. And when these bombs were dropped over the city of Hiroshima and Nagasaki on 6th and 9th of August 1945, well, there was destruction all over the twin cities. Still, if we go to the jungles of Hiroshima and Nagasaki, the unused blocks of uranium which are still in subcritical dimension, they are found. So let's pray to God that these weapons are eliminated, and fortunately these bombs have never been used after that unfortunate incident which took place in 1945. So children, with this we come to the end of our class today. We'll meet again very shortly with nuclear fusion reaction. Until we meet again, goodbye.